In this module, we are going to look at strong and weak bases in many of the same ways that we looked at strong and weak acids in the previous modules. Our objective is to be able to write reactions associated with the dissociation of both strong and weak bases, as well as to calculate the pH and pOH values of the weak and strong base solutions. Just like we talked about strong acids and weak acids being strong and weak electrolytes, we can talk about bases in the same way. Strong bases are strong electrolytes. They dissociate completely in water, such as what we see here with KOH. If I prepare a solution of potassium hydroxide, when I look at the solution, what I see are potassium ions and hydroxide ions, not KOH molecules. Weak bases are weak electrolytes. Ammonia, NH3, is one of the most common examples of a weak base. When I put NH3 in water, what I get are primarily NH3 molecules in solution and a small amount of NH4 plus ions and hydroxide ions. We can look at this list to look at some examples and make some generalizations about the type of compounds that are strong bases and those that are weak bases. When I look at the hydroxide compounds, here we have lithium, sodium, calcium. We've already seen potassium hydroxide, but there are others. These are our strong bases. When I put those compounds in water, they completely dissociate. So I end up with my ions present in solution and none of the original compound. When I look at my weak bases, there are kind of two classes of weak bases that I see. My ions, such as carbonate and bicarbonate ions, and amine-based compounds, such as ammonia, NH3, or pyridine. When I look at the Kb values of those weak bases, I see that the Kb values differ. So if I look at the Kb values, the higher the Kb value is, the stronger the base. So of the four listed in this table, carbonate will be my strongest base because it has the highest Kb value. Pyridine has the lowest Kb value and therefore will be the weakest base of these four. So let's look at an example of how we can figure out what the pH is of a solution of a strong base. For a strong base, we can assume complete dissociation. This lets us write the reaction as calcium hydroxide, completely dissociating or ionize into the calcium and hydroxide ions. Note that we do have a 2 as a coefficient in front of the hydroxide because we need a balanced chemical equation. Now I need to look at how much hydroxide I'm going to have in this particular solution. If my concentration of calcium hydroxide is equal to 0.250 molar, then what I find is that my hydroxide concentration is actually twice that, because for every 1 unit of calcium hydroxide, I end up with 2 units of hydroxide ions. So I take my 0.250, multiply it by 2, and get 0.500 molar for my concentration of hydroxide. Now I can use what I learned in an earlier module about finding pOH, and say the pOH is equal to the negative log of the OH minus concentration, which in this case is 0.500, and my pOH is going to be equal to 0.301. I can then find the pH because I know I'm at 25 degrees Celsius, so I know that pH plus pOH will be equal to 14. I plug in the pOH value of 0.301, and I end up with a pH equal to 13.699. When we look at the amine-based compounds, we can see a variety of options. We see our ammonia, which has 3 hydrogen groups. We see ethylamine, which has an ethyl group, which is a 2-carbon group, and 2 hydrogens. Or we can see something such as pyridine, which is a ring of carbon atoms. All of these are considered weak bases. Let's look at an example of how we use this. Aniline is a weak base. The Kb value is given as 3.8 times 10 to the minus 10th, and we're looking to find the hydroxide concentration of a 0.200 molar aniline solution. Now I'm not worried about what the specific formula is for aniline. I know it's an amine-based compound, but more importantly I know it's behaving as a weak base. So I'm going to use the abbreviation B to represent that weak base. So I have B standing for base plus water, And I know that bases are going to act as a proton acceptor, so I'm going to make my product BH plus OH minus. My law of mass action then becomes BH plus times hydroxide concentration divided by my base concentration at equilibrium. I don't include the water because it's in the liquid phase, and pure liquids are not included in the law of mass action. Now, to solve this, what I want to look at is setting up an ice table. I know that I'm going to have an initial concentration, a change in concentration, and an equilibrium concentration. My initial concentration of my base is given as 0.200 molar. For water, I don't worry about that. It doesn't have a concentration because it's a pure substance. For BH plus initially is 0. For OH minus is initially 0. My change will be minus X, and plus X. My equilibrium concentration is 0.200 minus X, and X. Now I can use the information that I'm given to solve for my value of the OH minus concentration. If I look at my law of mass action, I can substitute in X for both BH plus and for OH minus, so I have X squared over 0.200 minus X, and this is equal to our Kb value of 3.8 times 10 to the minus 10. I can make the same simplifying assumption that I did in earlier modules and say that X is much, much less than 0.200. Given the value of the Kb and that it's 10 to the minus 10th, this is going to be a very safe assumption. Such a small Kb value indicates that the reactants are heavily favored. So now I have 3.8 times 10 to the minus 10 equals X squared over 0.200. When I solve for X squared, I end up with X squared equals 7.6 times 10 to the minus 11th. I take the square root of that, and I find that I get X equal to 8.7 times 10 to the minus 6th. It's that X value, which is also my hydroxide concentration. Now, by knowing this information, I can then find the pOH of the solution, but I could also find the pH or the H plus ion concentration by using the calculations we used with the Kw value. Now that we have the OH minus concentration, we can look at a problem that will allow us to find the pH of that solution. You should have gotten a pH of 8.94. Now we can use that OH minus concentration that we found earlier, which was 8.7 times 10 to the minus 6 molar. And we can take that information and find the pH. We can take the pOH first, which is the negative log of 8.7 times 10 to the minus 6th. So pOH will be equal to 5.06, and pH plus pOH, which is equal to 14. So I know that pH plus 5.06 is equal to 14, giving me a pH value of 8.94. This makes sense because we're talking about a weak base. We are expecting a pH greater than 7, which is what we see for a basic solution. If we chose, we could also take our hydroxide concentration and say that Kw is equal to H plus concentration times the OH minus concentration, and we get 1.0 times 10 to the minus 14th equals our H plus concentration times what we calculated, which was 8.7 times 10 to the minus 6th. From this, we can get our H plus concentration, which is 1.1 times 10 to the minus ninth. And I can then take the negative log of that value and get that we have 8.94 as our pH, which is what we would expect since we're calculating the pH of the same solution. Now we can look at the relative strengths of an acid and its conjugate base. What we find is that the weaker the acid, the stronger its conjugate base. When we look at our spectrum of acids here, when we get to something down here like NH4 plus or HCO3 minus, we see that our conjugate bases of these substances are on the strong end of the bases. When we look at a stronger acid, we see the weaker its conjugate base is. So for HCl, we see its conjugate base, Cl minus, is actually so weak that it's considered neutral. One place where this will come into play is when we start to look at salts and trying to determine the acidity or basicity of a particular salt. Let's look at an example to determine which anion is the weakest base. Here we're given 4 anions and we're given 4 K values, but note that we have 3 Ka values and 1 Kb value. For our answer, we actually get something that's such a weak base that it's in fact considered neutral. When we look at this, what we want to look for is the substance that is the strongest conjugate acid because we want to find the weakest base. And so in comparing our acids, HCl, HF, and HCN, we see that HCl is the strongest acid because it has a Ka value much, much greater than 1. And so Cl minus will be the weakest base. Remember that the stronger the acid, the weaker the conjugate base. In the next module, we're going to look at the acidity and basicity of ions and how they behave as salts.